Okay, guys, good afternoon. Let me share my screen. Can you see the presentation?
Yes.
Okay.
Yes.
So I didn't know quite what kind of spin you want in this presentation about the company and how the company came up and succeeded. So I will talk, this presentation has a lot of technical information, but I will try to skip the over detailed technical and emphasize perhaps market aspects and other things. So we are Bright. The company is headquartered in Thessaloniki, Greece, with R&D in Greece, in Patras, southern Greece, and business development in US, France, Egypt, Netherlands, Spain, and India. We are a team of actually 24 now, of specialized people, primarily chemistry, physics, and electrical engineering. And when I founded the company, since I used to live in the US for over 30 years, I made it like an American company where most of the employees get a shareholding position as an incentive to working for the company. Our technology is patented in terms of materials and composition, deposition methods, and product assembly. We have right now 18 patents and trademarks at different stages. Most of them are granted, but we have some pending. And we have received numerous national and international innovation awards. Here on the left right-hand corner, you see us with the ambassador of the US to Greece, where we won first place position in the Greek American Chamber of Commerce Innovation Challenge for technology. So how the company came about, in my last job, I was working with Applied Materials, building factories worldwide for making solar panels. And when I left Applied Materials, I was thinking about this water, energy, and food nexus that the world faces, where food production through agriculture consumes 70% of water globally and 14% of energy. And then in order to sustain the world's population with the expected increase to 9.7 billion by 2050, we need to increase food production by 70 to 100%. Obviously, that cannot be done with conventional means. We need more technology, because otherwise there will be no water for the humans to use. And the most prominent technology is greenhouse farming, that essentially increases yield by 10 times while using 10 times less water. However, the penalty is energy, using 10 times more energy. And the energy component is 28% of the operating cost of the greenhouse. So that was the problem that we set out initially to solve. How do you make a greenhouse energy neutral or self-sufficient? Of course, that plays also to the climate change and the effect on agriculture in open field, because you have higher temperatures that have an effect. We have longer growing seasons, more extreme weather all over, water variability. The water dry areas become wet, wet areas become dry. And farming has been always a risky business, and of course climate change makes that risk even higher. You see the press front pages of the effect on climate change. We have this problem in Greece this year because the olive oil price has been almost the price of whiskey because of destruction of the crops. Same thing for grapes in 23. So these are very expensive. So what is the solution? And we're thinking about the solution. It's something called agrivoltaics. Rashid talked about that already. And agrivoltaics come in two versions. One is greenhouses, of course, complete enclosed environment where you control everything in terms of climate. And you see that one in the bottom picture. And the other one is open field, where you essentially establish a canopy over the crops so that you can protect the crops against weather, and at the same time you have the opportunity, depending on the configuration, to collect rainwater and therefore manage the irrigation of the field. And what we want to do is to produce a product that can be installed as essentially the canopy. So in open field, you have fixed mount, and sometimes people try to use opaque or regular solar panels or transparent solar panels, and in some cases use trackers. The traditional solar panels are opaque. They have large shadow, and of course they reduce the growing area, and of course anything that is under the panel and is shaded, the crop yield is affected very, very significantly. Crops require uniform light. You see that one through a science experiment on the right hand side. The crop, the plant always will find a way to go towards light. And if you use regular solar panels on the left upper side, you see the panel placement, but you see the shade underneath. That will have a significant effect on crop yield. If you use our technology, which is semi-transparent solar panels, you see uniform lighting in the greenhouse underneath, and our aim is to not to affect the crop yield negatively. So that's our solution, and the solution is essentially modifying the transparency of the solar panel to fit the location of installation and the crop yield, meaning the minimum light required for the crops in order not to be affected yield-wise. But we also do something else. We coat our panels with nanomaterials that we have invented that do absorb UV light, which is useless or harmful to plants, and shifts it to the red region of the visible spectrum where the plants photosynthesize, and specifically to the between 600 and 650 nanometers, where it is what is called chlorophyll B by the agronomist, and that essentially increases the photosynthetic active radiation the plants see, and therefore increase the plant yield. The solar cells we are using are bifacial monocrystalline solar cells, half-cut M10 cells, and as I said already, the glass transparency or the panel transparency is adapted to the location of installation plus the crops under the canopy. So these are two different pictures of two different panels. In one, on the left-hand side, the panel is very transparent, 80%. On the right-hand side, it is less transparent, I believe 50%. So the nanomaterials, as I said, are developed by us, and they are applied on glass by using inkjet printing. And there are two main categories of materials. One is anti-reflective nano coatings that essentially increase the transparency of the glass, and you see the difference when the glass is not coated versus coated. But at the same time, we are increasing the transparency of the glass. We also make the glass hydrophobic, meaning that rainwater is removed from the glass very quickly and doesn't stick on the glass, so that the reflectivity is not increased, and also the glass doesn't soil very easily. The second coating we have is what we call luminescent solar concentrator. And this coating is a coating that absorbs UV light and retransmits it in the red region of the spectrum. You see a picture depicting the effect on the right-hand side where you see a glass over a bed of UV lamps. So when the lamps are off, the glass looks like regular glass. When the lamps turn on, the glass becomes red because it absorbs the UV light and transmits in the red. And on the diagram down left, you see the spectral response of the coating. We have another one that we do the same thing. We absorb UV, but we shift it to blue. And the reason for that is that the plants photosynthesize in two different regions. They are called chlorophyll A and chlorophyll B. The blue region is between 400 and 450 nanometers, and the red region at 600, 650 nanometers. And we have a coating also that combines the two, so the same coating shifts both to blue and red. The spectroscopic response of these coatings has been verified by third parties. The interest here is not from the energy point of view, but from the plant growth point of view. So we selected Wageningen University, one of the most prominent agro schools in the world, that they measured our glasses, and they gave us the results where they show, especially on the red shift, an increase in transparency there, or increase of the active photosynthetic energy of 9%, which is very, very significant. Here's a science, not actually a research project done by the agronomy school at the University of Patras, where they grow in a controlled light environment in a cube. This is tomatoes, I believe, in coated cube and uncoated cube, and you see, you can tell which one is the coated is on the left-hand side, because in the same amount of time the plants grow bigger. And of course, there are other measurements in terms of dry weight and wet weight of the plants and so forth. They've done this experiment with tomatoes, eggplant, oregano, sage, and I think parsley. So the coated glass offers higher cell efficiency, but also power performance. And the anti-reflective hydrophobic will be on the outside of the glass, and then the LSC coating on the inside of the glass. This shows you the effect also of the coatings on the solar cell efficiency. We have almost 1% increase in the solar cell efficiency because of the higher light absorption by the solar cells affected by the coatings. So for the agrivoltaic optimization, we essentially do the energy production that an agrivoltaic installation will use in order to essentially offset the energy uses for pumping, tractors, lighting, environmental. All the farming equipment will become electric in a few years. And of course, the crop protection that will mitigate climate change. So what we have, actually our product is a cultivar-specific solar panel, optimization of transparency power generation. Transparency goes from 30 to 85%, and the max installed power in the panel goes from 300 watts to 115 watts per panel, respectively. This is a crop-specific support structure. In the support structure, you have to take in consideration the working height, but also the lines between the crops and the distance of the crops in the same line, and then the amount of air the particular crop under the canopy needs in order to grow. This is also that was show you. The previous slide was one line. This one is an actual canopy. We have essentially installed in several places both greenhouses and agri-PV installations of the various crops. You see here a tomato greenhouse, there is a grape greenhouse, there is ornamental flowers greenhouses, and then in open field over grapes, over pears, over strawberries, over blueberries, and so forth. We have actually installed in 10 different countries over various crops. And this is very useful because we collect data for the interaction between crop and panel, which is very, very important in our business. Another effect by using this technology is that you can reduce severely or even turn zero or negative the CO2 footprint per kilogram of crop produced, which is a very important marketing tool for, especially for the markets in Central Northern Europe and Northern America. And in a pilot greenhouse we did over grapes, we found out that the CO2 footprint was negative per kilogram of grapes produced. In open field, we have, of course, better protection for the crops in terms of wind, rain, hail, snow. Temperature modulation. During the summer, we are 2 to 3 degrees lower than the environment, and during the winter, 2 to 3 degrees higher. Pollinator protection. This is also very important because in some cases, when they use bees, for example, to pollinate the crops, if you hang the bee system under the canopy, then the bees can work under any weather conditions because they are not affected. We collect and give to the farmer the rainwater, so there is a water management, and we can integrate in the open field bird netting that can automatically drop on the sites and then enclose essentially the plants within that environment. And you see some crops here. We've done grapes, several kinds of berries, and in the course of this program of Solar Hub, we will install over peaches. Besides doing the panel, we also do the design of the project and then the system design. We place the panels in different strings with different MPPT points depending on the orientation of the panel, south, north, east, west. And then depending on the orientation of the panel, we monitor the performance of the panel in terms of energy production on different strings. And here you have a snapshot from the inverter portal where in real time we know first of all what is the weather, because we connect a weather station to the inverter so that we know exactly how's the weather there, and we monitor the energy produced in real time, the monetization of that energy depending on what kind of system we've built, like self-consumed or in terms of net metering, or if we sell it to the grid, at what point we sell it. And then, of course, the CO2 savings in terms of avoidance. The impact results of what we're doing is the energy generation, in fact, exceeds our expectations based on simulation prior to installation. And this is due to the fact that we have a better temperature coefficient for the panels, since we install at higher height than regular PV. Regular PV, you are, let's say, half a meter from the ground. Our panels are in greenhouses 8 meters high, in agri-PV a minimum of 4 meters high. So no negative crop yield, only positive impact, which is extremely important for the farmer. And this is actually our first conditional parameter that we face when we design a project. Severe reduction in the CO2 footprint per kilogram of crops produced, and the farmer has an additional revenue stream from energy sales or self-use from the greenhouse or the open field structure in addition to the crop revenue. If you want to see the dramatic potential of this technology, let's say in Europe, and we want to make it dramatic by exaggerating a little bit on the uptake of the market. But let's take a single crop, that's grapes, which is very popular in Portugal, Spain, France, Italy, and Greece is the largest European producers. And assume 50% penetration, market penetration, to make it dramatic. That's the dramatic part. The energy production of that will be over 1 million gigawatt hours per year. And the CO2 emissions reduction, 677 million tons per year. And the revenue from the energy sales, 42 billion. So assuming 4 cents per kilowatt hour for grid sales, which is what is the system paying in Greece right now if you connect to the grid. So that shows the potential of the dual use of land, essentially, for agriculture and solar energy production at the same time. So that's a presentation, but if I knew, then I would I would offer some slides essentially on what are the calamities for starting a company and developing a company. I mean, this company was started by me. Of course, I have extensive experience. This is my second startup, and I was the seed investor. I had the audacity to start the company during the Greek financial crisis, which was extremely difficult. So I had to be the seed investor, and then we raised Series A capital. After we built some value in the company through R&D grants, because building value in the company and increasing the company valuation allows you to keep more of the company percentage into the founders. So we raised Series A of 9 million in order to build a manufacturing facility here in Greece for making these panels that have the nano coating materials in them. And this line this factory that will combine the coating of the glass and the panel assembly will be the first line in the world that operates like that. So the biggest problem in doing, of course, this thing in Greece is the regulatory framework and the bureaucracy of the country. It would have been much easier if we did it, let's say, in Germany, Holland, or even better in the US, where, of course, I'm very familiar with the environment, so I would prefer that. But we are here, so we have to deal with it and hope for the best. Now we have the headache of building a factory, which is not a small task. A lot of headaches, and most of the headaches, stupid headaches like permitting, fire protection, and zoning, and a million requirements imposed by the regulatory framework. So that's all I have, and if you guys have any questions, you have my contact. Let me know, or you can ask now, or whatever you prefer. Thank you.
Thank you, Nikos. Thank you for this very interesting story of Bright.